Hello, everyone. I'm Fernando Pereira, a professor in the Computer Science Department of the Federal University of Minas Gerais. And today I will talk about how innovation happens in the design and the implementation of compilers and other programming language tools. And I shall start this talk trying to answer this question. How do you perceive innovation in compiler development? But before we answer this very specific question, let's try to answer the most general version of it. How do you perceive innovation? At least innovation in computer science. The answer in this case is easy, as innovation in computer science today is part of the collective consciousness. We all more or less know how innovative computer science is. It suffices to remember that it has not been 100 years since we had computers. Take ENIAC, for instance, one of our first computers ever. Now compare it with a smartphone. I chose a model from 2021, but any model from recent years will do for this comparison. In terms of price, ENIAC would be almost 10,000 times more expensive if we account for inflation. And ENIAC would be much larger too, 155,000 times heavier. It would consume about 50,000 more power. If we talk about computing capability, the contrast is even greater. ENIAC had 200 bytes of memory, give or take, and it was way slower. A modern smartphone is about 3 billion times faster than ENIAC, costing almost 10,000 times less. But that discussion was about computer architectures. Now let's shift on to programming languages. Let's ask the same question, but it's time about innovations in programming languages. How do we see innovation in this domain? Well, let's consider Fortran, which is one of the oldest programming languages. Here's an example of a Fortran program, which computes the factorial of an integer n. Here's the same program, this time in Fortran 90. It didn't change much. The loop is still there, variables are named more or less in the same way. We have this block structure with keywords and an terminal. The same assignments, we do have some differences, of course, like the type annotations. Early Fortran would use the name of variables to determine their types. That turned out to be a bad idea, and modern Fortran now use annotations. But then you might say, okay, that's the same program language. What about a newer language? Let's take Rust, for instance. That's a Rust program from 2012. You see, syntax didn't change much. These loops and assignments are pretty much the same thing. We certainly don't see innovations in programming languages that we see in hardware. Why is that? Why do programming languages evolve so slowly if compared with computer architectures? Why can't we have a kind of Moore law for programming languages? Well, for one, natural languages, they evolve very slowly. I'm giving this talk in English, but my native language is Portuguese. These two languages come from a common ancestor, which is the Proto-Indo-European language. It was spoken some 7,000 years ago, more or less. Portuguese itself came from a newer language, which is Latin. Latin was the language spoken in most of the Roman Empire as late as 1500 years ago. Then we have what's more or less the precursor of Portuguese shaping up at about 500 years ago to give origin to modern Portuguese, which is the language that I use to chat with my wife and my son, my family. You see, that's all a very slow process. Programming languages, of course, evolve faster than natural languages. For instance, Fortran was invented in the mid-50s. That's only about 70 years ago. And we are talking about what's possibly the first programming language to ever become popular among programmers. And about 20 years after Fortran, we had C, which is still one of the most popular programming languages in use today. And we are talking about a language that appeared more or less 50 years ago. Rust, of course, is much newer. Graydon Hoare started working on it less than 20 years ago. So let's get back into our question. Why do programming languages evolve slowly, or at least slower than hardware architectures? Well, for one, programming languages solve stable problems. They exist let to let us code algorithms, and algorithms don't change that often. Of course, programming languages do change to accommodate development in software engineering and new programming trends, but the algorithms, at least the algorithmic thinking, essentially remains the same over the time. And then we have issues with human cognition. There is not much room for a very different programming language. Humans still use languages in pretty much the same way since we acquired the capacity of communicating in structured ways. There is also a question of economics. If we invent a totally new programming language, then we would have to teach people how to use it. And that's a lot of time. Training people costs money because that requires time. It would be very unlikely that a language with a much different syntax, for instance, would ever become popular. Of course, it happens once you consider language such as Prolog, for instance, but that's, very rare. And finally, there is a question of ecosystem. A language does not exist alone. It requires programmers, libraries, and tools. The world of programming language is not very democratic. If we come up with a new language, we would have to come up with the right tool chain and would have to dispute users with languages which are already very well established. And then we might ask, what about compilers? How fast they evolve? Faster or slower than programming languages? Faster or slower than computer architectures? Well, they tend to evolve slower than computer architectures, but not much slower. A very different computer architecture would require a compiler as well, but they evolve faster than programming languages. The compiler is a tool, evolves faster than the language that the compiler compiles. For instance, let's look into major C standards. Each new standard would bring something different into C. That's more or less a proxy for the evolution of the language. Since 1989, we have about 5 major standards being released. Releasing a new standard is complicated. There's a lot of talk that goes in the community must accept it. It's not that simple a task to release a new standard. But if we look into a compiler infrastructure like LLVM, we shall see more than 100 releases since 2003 when the compiler first came out. Granted that some of these releases were minor, but still, there is a lot that's happening in the implementation of LLVM all the time. And yet, if we look into the optimizations that LLVM carries out, we shall see that many of them are old ideas. For instance, in 1971, Allen and Koch published this report, a catalog of optimizing transformations. In that report, they describe optimizations such as inlining, loop fusion, and efficient, common subexpression, elimination, commotion, constant propagation, and more. Well, these still form the backbone of the optimizations that modern compilers implement. If we look into a more recent book like Rune, which is from about 2012, we recognize most of those optimizations from Allen and Koch. We might see some new keywords like static single assignment form, data flow analysis. There will be more emphasis on type systems and vectorization, for instance, but the old optimizations will be there. And that asks for the question of how can we quantify this progress? What's the improvement that we get today using compiler optimizations? This question is not very difficult to answer because compilers have optimization levels like O0, meaning no optimization, and then O1, O2, O3, and such. Both GCC and Clang feature these 3 optimization levels, O1, O2, and O3. Let's see what they give us when we apply them on the programs in Spec CPU 2016. Let me show you the speedups over O0. I'm taking these numbers from an experiment made in 2019 in its paper about instruction visibility. At O0, GCC does not apply optimizations. Well, it does local constant folding, for instance, but it does not really do, for instance, global register location. All the variables in this case are mapped onto the stack. They are loaded in registers just to perform operations and then stored back in the stack. Anyway, here's the result of the optimizations. As you see, we observe speedups in most samples. Some speedups are huge, indeed, almost 6 times sometimes. If we look into averages, we see that minus O1 improves speedup by 2.27 times, more or less, minus O2 by 2.44, and minus O3 by 2.46 times. That's more or less what we call Probstein's law. Todd Probstein was a professor at the University of Arizona. He retired this year, which is 2025. He became famous for the Probstein paradox, and by Probstein's law. We care more about the law. It says that the power of compiler optimizations doubles every 18 years. 18 was chosen more like a parody of Moore's law, but it kind of worked if we imagine that C is from 1972 and that today GCC minus O3 more or less gives us, 2.5 times speed up. So where does the speed up come from? I mean, what's really innovation in compilers? How does a compiler can improve program speed by 2.5 times, even more than that sometimes? Well, there's a very nice discussion about it in Stefanos Basiotti's webpage. He talks about different compiler optimizations, giving examples, which are very nice. One of the coolest examples in Stefanos' webpage is about how Clang optimizes this function, which exercises the Collatz conjecture. The conjecture asks whether repeating two simple arithmetic operations will eventually transform every positive integer into 1. Well, the function itself is not super important. What really matters is the control flow graph that we get when we compile the function with Clang minus O0. It's the CFG on the left. Nothing really very special about it. There's a simple loop, just like in the source code. Now, the magic happens once we compile this program with optimizations enabled. We can use Clang minus 1, for instance, that will do the trick. And that's what we get. For Collatz of 249, Clang simply returns for 7, the number of iterations that it takes to transform 249 into 1. And if we try an older version of Clang, say Clang 17, then we are back into the loop. Clang 17 can't solve this computation statically. By solving a computation statically, I mean to say that Clang 20 at minus 1 knows that the program would return for 7 and folds its number right into where the call would happen. But that's only with numbers up to 249. At 250, Clang minus 1 is back with the loop. So what's happening? Well, that's a product of an optimization called scalar evolution, which did not exist at the time Allen and Koch wrote their catalog of optimizations in 1972. If we look into Clang source code, we shall see lots of papers that have inspired this optimization. We see papers because the academia influence the industry, at least in design of compilers. But the industry influences the academia too, as we will see in the next part of this talk. So that's it for the first part. If we have questions, we can send me an email. And thank you for your attention.